So of the functional groups we can make from carboxylic acids, possibly the most important is the formation of amides. So in other words, here we're talking about the addition of a carboxylic acid with an amine to form an amide. And the ability to form amides like this, very, very important reaction biologically, because while biological systems do it very differently than the way we might do it in the lab, it's reactions just like this one that are what allow us to build up proteins. Proteins are formed through peptide bonds. Those peptide bonds are the bond of the amine of one amino acid to the carboxylic acid of the next amino acid. What makes this reaction more complicated synthetically are we can't use a lot of the types of conditions that we will normally see for acyl substitution. So we cannot do the following. We cannot use basic conditions, which would give us RNH minus, because this will just deprotonate the acid. And if we've deprotonated the carboxylic acid, at that point, it's not going to be able to serve as an electrophile. We also can't use acid because that'll protonate our amine. And if we've protonated the amine, that's going to make the amine into a very poor nucleophile. So instead, for this reaction, we generally use a reagent known as DCC. DCC stands for dicyclohexyl carbodiimide and has the following structure. And so as I go through the mechanism here, I'm not going to draw out the cyclohexane rings each time because it'll just make our drawings more cluttered. So I'm going to abbreviate the cyclohexane rings as CY. And so our DCC will get drawn like this. All right, so how does this work? So we start with our carboxylic acid. And here's our DCC. And one of the nitrogens on DCC will remove the carboxylic acid proton. Very much like the protonation of a carbonyl for nucleophilic attack, we've essentially done the same thing here. We've activated that carbon in DCC for a nucleophile, and it's going to be this O- that will attack here, shift the electrons up onto nitrogen. And as we've seen many times, and we see with many reactions, a large part of the reason we need to do this is, we're trying to substitute for that OH group. And hydroxide, we know, is not a good leaving group. But by attaching this other thing on there, we're going to see for a couple reasons it's going to benefit our reaction significantly. So at this point, we can add an amine. In this case, I'll use aniline as our nucleophile. The lone pair on nitrogen attacks the carbon of the carbonyl, and we shift the electrons up onto oxygen. This, as we see for many acyl substitution reactions, will make our tetrahedral intermediate. At this point, that positively charged nitrogen is going to lose its proton. It's become neutral, so let's copy the structure down to the next page. So again, all we're doing here is we've lost a proton. Now the O minus adds its electrons back in. We kick out the leaving group, and those pi electrons will pick up a proton from somewhere, presumably one of the amines that's given up a hydrogen. And we formed our product, which is an amide. And we formed this new carbon-nitrogen bond. In addition, just to point out the byproduct, the byproduct here, dicyclohexylurea, actually makes it very easy to monitor this reaction. Most solvents that we would run this reaction in, the dicyclohexylurea is not soluble. And so that helps not only by removing our leaving group from the solution, which helps push our equilibrium forward, but also, when you set this reaction up, everything will be nice and dissolved in solution, but by the time the reaction's done, you'll see all this powder in your flask, and you'll know that the reaction has progressed.